I think by 2030, 2035, we're going to have more and more gene therapies. I'm hoping that we will cure cancer, and especially with all the immuno-oncology coming online. I believe that by 2035, we're going to see a lot more cures, which is going to be pretty amazing.
I think eventually we'll get into the conversation of this space and scientists trying to play God. I think that ethical question will probably happen or come sooner rather than later. What happens then? Yuta Lee is a biotech innovator and founder of Accelerated Bio, which is advancing stem cell therapies for human regeneration. His work with trophoblast stem cells could revolutionize how we repair and enhance the human body.
And so my big ask to everybody is find a way to invest in longevity, especially if you're a billionaire. I mean, what is beating the S&P 500 for the next 15 years going to help? Nothing. You can't take it with you, right?
I get a lot of pushback sometimes from comments saying like, this is the devil's work, this is just for the billionaires. What would you say to them? The future looks amazing, but also a little scary. If you, just like me, want to have an honest outlook of what the next chapter could look like and how best to prepare for that, I ask for one simple favor: subscribe, so I can invite the brightest minds on this podcast and get those answers for both you and I. Enjoy the episode. Why should someone, regardless of age, background, class, whatever, need to or want to learn about stem cells?
Well, it has to do with everything that's happening with society today, right? If you look back at history, we've come along with about 200 years of healthcare being based on chemical drugs, and that's brought a lot of great advantages, but we are realizing that, a lot of these small molecules or even monoclonal antibodies, even though very effective in many cases, they are palliative at best, meaning they're really only stopping a protein process so that the symptoms will go away. I think cell and gene therapy, especially stem cells, is coming along and proving that we can actually cure a lot of these diseases. And with chemical drugs, over the last 200 years, we're taking hits with the liver and the kidney. There's a lot of toxicity issues. But with cell and gene therapy, it's all very natural. So we believe that this is the next generation of healthcare. And, there are already many gene therapies and many stem cell therapies going through the FDA and the EMA and various regulatory bodies around the world, actually making cures. So I think everybody should pay attention and learn more about it.
Can you just explain that as if I'm your daughter's friend?
Right.
When it comes to chemical drugs that someone might take, let's give an example of why someone might take stem cells. Could it be that they're suffering with some form of cancer and they're maybe going for chemotherapy? Like what is a good example of how stem cells would be a great alternative to, let's say, just any chemical drug?
Gotcha. Well, stem cells, you can use it in two main ways. You can either create effector cells. These are your own, like immune cells, to go kill something. Or you can take a stem cell and differentiate them to the organ or cell type of the organ that you want to fix and use that cell to replace or fix bad situations. Like, for example, if you have a liver that's failing, then you can take a stem cell and differentiate or turn them into liver progenitor cells or liver cells and basically inject it into the liver to have it be replaced and therefore fix your liver issues, right? Chemicals, for example, if you have a infection, if you have, let's use a very simple one, allergies, right? When you have allergies, you can take a pill and it basically, that small molecule will block the functions that will turn into a symptom of sneezing, tearing the eyes, etc. but you're still allergic to whatever you're allergic to, right? And so the main cause hasn't been solved, but you have stopped the symptoms. In cell and gene therapy, you're literally going in and fixing the original problem. And once it's fixed, hopefully it won't come back again. And that's what we're hoping for. And we believe that this is the next, era of healthcare, where we can go and really fix a lot of things. And if you think about it, like, look at all the healthcare systems around the world. They're struggling because healthcare costs are going up. Drug discovery costs are going up. And with more population coming, it's just unbearable. I think the whole system just cannot take it anymore. And so you really need to find ways to cure issues instead of just stopping symptoms, in which case you're just taking more and more drugs. Yeah. Right? Yeah.
Why did you feel called to enter this space?
I'm sorry, say again?
Why did you feel called to enter this space?
I kind of came in a little reluctantly, I have to say. So my father, who's an MD, PhD, he got his MD in Tohoku University in Sendai, Japan, and a PhD at St. Bart's University, London, right here in central London, in the late 70s. And he discovered a stem cell platform called a human trophoblast stem cell, which we source from an ectopic pregnancy. Now, give me a minute to explain this. An ectopic pregnancy happens when the embryo is traveling down a fallopian tube and it gets stuck. And it'll sit there and grow until it bursts the tube. And if it bursts the tube, the mother may die of internal bleeding, right? And so typically what happens is a woman will feel a sharp pain, go into the ER or emergency room, get scanned. The doctor will say, ooh, you have an ectopic. We have to take it out. And they schedule an emergency salpingectomy in which they ablate or burn both sides of the mass so that it won't bleed. They use a scope to remove the mass, and all they have to do is give it to a pathologist to look at, and they confirm it, and they can throw it away. And the reason they throw it away is because a healthy pregnancy, the embryo typically needs to implant into the mother by day 7 or day 8. But you don't discover an ectopic until 4 to 8 weeks after, right? So there are many weeks in between where that embryo is not attached to the mother. There's no nutrients coming to it. So OBGYNs understand it to be non-viable. The fetuses are non-viable, okay? And so you have to remove it to save the mother, because if it bursts, then you have internal bleeding, sepsis, etc., and also the fetus is non-viable. So in this way, he discovered literally the earliest stem cells that you could possibly find without any ethical issues, and we call them human trophoblast stem cells. And so in 2005, he came to me and said, Yuta, you're the business guy, do something with this. And I said, dear God, okay. So I had to take it on. And so I created a company around it, and I've been trying to commercialize it ever since.
How did he discover that? It's like, how did he speak to the physician in the ER room and say, look, I want to test on this. Right. Because it just feels like such a faraway thing to even start thinking about.
That's right. Well, he is a surgeon. So he's an MD, PhD, and, he does research half the time, and he's, in a clinic half the time. Right. And so I think it takes an MD, PhD who understands research and also has their hands in the actual clinical process to be able to figure something like that out. So we got very, very lucky. And so, when he was performing this salpingectomy himself, he was thinking to himself, why are we throwing this stuff away? There's got to be amazing things in here. But to avoid all the ethical issues, he scrapes off the preplacental tissue, then hands the mess back to the pathologist, who looks at it and throws it away. So we got very, very lucky that he was the first one to discover this.
So the preplacental tissue versus the human trophoblast stem cells, like, what is the difference?
That's the same.
Okay,
Yeah,
it's the same. Okay.
so the human trophoblast stem cells are from the preplacental tissue
Okay.
of that ectopic mass.
Okay.
And so basically we harvest the preplacental tissue and then we give the rest of the mass, which is the non-viable embryo, to the pathologist who then discards it.
Okay. So the embryo itself is discarded.
That's right.
Okay, so you've got the preplacental tissue.
That's right.
So what is the difference between stem cells and then human trophoblast stem cells? What are the other companies' surgeries using at this point?
I get what you mean.
And I just want to pause here.
Yeah.
I've been told by strategist people that I'm being too intellectual and not trying to bring this back to every person to understand. So that's why I'm trying to explain everything in layman terms as well.
Yeah, no, this is great. This is great. This is what, everybody needs to hear actually.
Yeah.
So I'm going to start with typical fetal development. So basically how babies come about. Okay. So in the first 8 weeks, when a woman is pregnant, right? The first 8 weeks, the embryo is literally just lumps of cells. Okay. From 8 weeks to 38 weeks, that's called a fetal period. So from 8 weeks to 38 weeks, that's literally when the body's forming. You and I, that's all we all came from there, right? So the baby's forming, and at 38 weeks, the baby's born. Okay, so that's the birth event at 38 weeks on average. And then everything after that is considered adult. Okay, so where you get stem cells from, the earliest stem cells you can get from an IVF clinic. It's called human embryonic stem cells. So in an IVF clinic, what happens is, a woman trying to get pregnant will inject herself full of hormones, and then she will produce a lot of eggs, right? And they will inseminate the father's semen or sperm into these eggs to create embryos outside of the body. Okay. And what you would do is you find the healthiest embryos and you implant that back into the woman, and hopefully she'll get pregnant. Okay. But, when they do this process, they probably harvest 15 to 20, God knows how many eggs, right? So there are a lot of embryos left over that they freeze. And back in 1998, I believe, a professor named Jamie Thompson in Wisconsin thought, hey, we could probably use this for research or, creating therapies. And so that's the birth of the human embryonic stem cell. That's the earliest you can find, okay? Then ours, right? 4 to 8 weeks post-fertilization, so still in the embryonic stage, so in the early stages, right, where they're just really lumps of cells. And then you can get a lot of cells or stem cells from the fetal period, but usually they're coming from abortions, so there are a lot of ethical issues. And then the birth event is where you get most of your cells, these mesenchymal stromal cells. You may have heard of MSCs, right? That's where they're coming from. So you get them from cord blood, the placenta itself, Wharton's jelly, plenty of cells to get, right? And then everything after that's adult. So you can get it from fat, you can get it from bone marrow, and then comes the Japanese that created the induced pluripotent stem cell, discovered back in 2008. That was published by Shinya Yamanaka, right? And so what he did was he was able to take a virus, take out all the bad stuff, put in 4 transcription factors, and put it on a fibroblast, which is an adult cell, and was able to transform that back to a stem cell state, right? Which is incredible if you think about it. So to take an adult cell and move it all the way back to a stem cell state.
What do you mean by stem cell state?
The earliest, most original cells that you could possibly have.
Gotcha.
Right? So we all came from that. Right? Every cell in your body all came from this early cell that then differentiates into various parts of your body.
Gotcha.
Like this cell will turn into a muscle, turn into an eye, turn into your hair, right? And so that's how we all came about.
Yeah.
Right. So the original stem cell. So, with these induced pluripotent stem cells, iPSCs, they were able to reprogram them to go all the way back. Okay. I personally think that that is probably the most impactful for longevity, right? Because before then, it was death and taxes, right? Everybody knew they were going to die. And, you can use religion, you can use philosophy to kind of make yourself feel better. But since that time, think about this. We can now reprogram every cell to go back to the original state. That means we now have the power to figure out, theoretically, how to make you completely younger all at once. So now it's just an engineering problem, right? And I believe in the next 10 to 20 years, a lot of scientists are working on this to figure out how to reprogram ourselves to literally just be younger.
Yeah.
Right? There are a lot of companies working on this. Very exciting stuff.
Let's talk about how one interacts with stem cells. As in, how does one inject stem cells? Where would they do it? What are the benefits of taking human trophoblast stem cells or getting injected with human trophoblast rather than something else?
Great question. There's many ways to answer that. But I want to start by saying this. I think, especially in the US or in the EU, there are a lot of regulations for this, right? And so these are advanced therapies that need to be approved by FDA in the US or EMA in Europe. And so you can't really just go into a clinic and just get injected with this stuff. So it needs to be approved therapy. You can go to third countries where there are lax rules, and some people have been doing that, but you really have to do your homework relative to the safety and the product itself, right? So, and it really depends on what your problem is. Is it joint pain? Is it, cancer? Is it liver issues? Who knows, right? So there are many ways to kind of approach this. In the US and in Europe, there are existing cell or cell and gene related therapies that can take care of leukemia, for example, right? And they're mainly called CAR T therapies, right? And what that is that they've taken your T cells, which is your own immune cells, and because they've lost the ability to recognize tumors in your body, right? They've literally engineered in a target in order to help the T cells recognize the targets. Then they grow all that out and inject it all in your body, and it has an incredible effects. I think really high percentage of remission rates, at least for 6 to 12 months, and the scientists are working on extending that to beyond 12 months. Yeah, but some people have actually had cures with these CAR T therapies. That's available now. Unfortunately, it's very, very expensive because they are autologous, which just means that you're taking your own cells, removing them, engineering them, and putting them back, right? Which is a one-on-one model, right? So this is very, very difficult to scale and very expensive. Right? So the first CAR T therapy in the US that came out was in the range of $470,000.
Okay.
Yeah. So pretty expensive. Yeah. Not everybody can afford that, right? So, what I'm trying to do is to figure out how to create a platform that is scalable so that we can really drive that cost down. And the only way to do it is to use allogeneic strategies. Allogeneic, as opposed to autologous, means that you're taking a healthy cell from a healthy donor and then manufacturing it to scale so that everybody can use it. So you have to overcome the immune issues, which we naturally can because we're preplacental cells. And preplacental cells have this special ability to dampen down the immune system for a very specific reason. So think about this. An embryo, right, is a recombination of the father's gene and the mother's gene. So how come this alien thing is able to attach itself to the mother without her immune system going, whoa, what's going on here? Get this thing off of me, right? It turns out the placenta expresses a marker called HLA-G that dampens down the mother's immune system. It goes, whoa, calm down. Don't worry about this. Let this thing stay attached, right? And is able to then draw nutrients from the mother to have the baby grow, right? And this HLA-G is so powerful that you can actually have an embryo implanted into a surrogate mother, a woman that's completely biologically non-related to the baby, and have that woman carry the baby to term. Is that incredible? So it's an incredible feat of science that we figured that out, right? So our cells, our human trophoblast stem cells, actually have this HLA-G expression, and so in this way, we believe that we are able to scale out our cells so that everybody can use it. Right. And our scale is pretty incredible. So because they're such early cells, from the embryonic stage, we're able to grow them out to 85 population doublings. So that means that imagine one cell turning into 2, turning into 4, turning into 8, 16, et cetera, 85 times, right? And at 85 times, that's e to the 25 cells. That's literally enough cells to grow 2 trillion human beings. So with this human trophoblast stem cell platform that we have, we're able to grow enough cells with the immune privilege characteristic so we can really scale everything that we do and make everybody, make it affordable for everybody to use.
So you don't need that much. You don't need that many examples, or as in how many human trophoblast, how many mothers do you need for this to work?
Actually, just one. And we already have that. In fact, we already have 17 different GMP compliant donor lines. Now, GMP just means good manufacturing practice, right? So both the EMA and the FDA uses these good manufacturing practice or GMP guidelines to make sure that the companies that are producing these therapies are manufacturing and documenting everything at the highest level so that the product can be super safe for human use, right? And so that's what you have to manufacture too. And so, if you're Joe from San Diego and you're looking into a company that does not have an approved product, no one can stop you from doing that, biohacking, whatnot, but you better look into how they're manufacturing it. If they're not manufactured to GMP, something can go wrong. Contamination, maybe some pathogens or some disease from the donor cells. So that could be a very big problem, right?
Okay. So how many tests are you doing?
A lot. So it starts from the actual donor itself, right, which is the mother. Then we have to test the cells. And throughout the entire process of manufacturing, you have to constantly test all the way to the very end. And then the final product, they call it the release, you have to do a whole bunch of tests, sterility, and make sure there's no contamination with bacteria, with other diseases, or human error, for example, right? So imagine if you did not have a controlled environment and somebody's growing these cells and you sneeze right into it. Dear God, what could happen, right? And you're trying to put that into your body. It's quite dangerous. So the whole process needs to be very sterile, very controlled, and very documented.
In theory, it sounds great.
Yeah.
Right. This whole idea that you have something scalable.
Yeah.
And something that can have an incredible impact on every human.
That's right.
A lot of people think of stem cells, and I can remember like a South Park episode back in the day. I don't know if you remember that episode,
I love South Park.
But they had an episode on stem cells, and they really
went
deep on this whole idea of ripping fetuses out and all that. And
Dear God.
they made a bit of a joke about it. But I think it's this inaccessibility that scares people, or gets people up in arms about this whole space.
Right.
So what you're saying is this is something very scalable. The bottlenecks right now is it safe?
That's right.
Do we have the right facilities to implement this?
That's right.
And really understanding like what benefit is going to have on a wider segment of the population. So let's just break that down. Like first of all, with this, like so you've mentioned leukemia and other forms of oncology and cancer. Like, what would be the benefit to Joe in San Diego or Emma in San Diego that are perfectly healthy? They're 35 years old.
Right.
Yeah.
Yeah, that's actually a great question. That's actually my goal, right? So, do you mind if I kind of go into a long story with this?
Please.
All right,
please,
perfect. All right, so my kind of path into the whole longevity field actually happened through the National Institute on Aging. So about 2 years ago, a researcher called me and said, "Yuta, I saw one of your presentations about your stem cells in Seattle, and I hear you have the earliest stem cells that you could possibly find without ethical issues." And I said, "Absolutely. In fact, we already manufactured them to GMP, so they're clinical grade. They're able to be put into human beings." And he said, "Wonderful. Can you send me all of your conditioned media?" Right? And conditioned media is basically just a nutrient-rich soup that you grow cells in, right? So you put it in a dish and you add this media, and the cells can use that nutrient to grow, right? To split and grow. And when it gets full, you have to split up the dishes and add more new media. And usually you just throw away the old media, but we kept everything. So I sent him 6 liters of frozen media.
Wow.
And then I called him up and I said, "What are you doing with this?" Right? And he proceeds to tell me this crazy story about these researcher, Irina and Michael Comboy. They at Stanford 20 years ago, they did this experiment called the heterochronic parabiosis, right? Heterochronic means different timing, parabiosis meaning together. So what they did was they stitched 2 mice together, right? So it would have one circulatory blood system, one old mouse, one young mouse. And they discovered that the old mouse was biologically getting younger and the young mouse is biologically getting older, right? They did a second experiment where they just did a plasma transfer of the blood. They just exchanged the blood without stitching them together. Same thing was happening. So what does that mean? That means the rejuvenation of the old mouse was purely the function of the proteins coming off the blood of the young mouse, right? And that gave birth to this idea that, these tech billionaires are running around with blood boys, right? So they're trying to get their young blood boys to donate their blood so they can stay younger. Well, what this researcher was thinking is, if that works, I wonder what would happen if you take the earliest stem cells and the secretome, or the proteins coming off of the cells, and applied it on senescent cells. Now, senescent cells are these zombie cells that we collect in our body as we get older. These cells stop dividing, but they refuse to die, right? Typically, when cells get old, they apoptose. They're supposed to just kill themselves. But a lot of these cells don't. And our immune system's not strong enough sometimes to hunt them all down. And so they start accumulating, and what they do is they start secreting a lot of inflammatory messages to the rest of your body. Inflammatory messages are all related to a lot of diseases that we have today. So what we need to do is either kill these cells, called senolytics, or control the inflammation, called senomorphics. Right. And so what we did in the last year was we did these series of experiments where we applied our secretome from the human trophoblast stem cells onto these senescent cells. And what we discovered is that transcriptomically and proteomically, we were able to systemically downregulate all of the inflammatory messages, the markers. Okay.
By how much?
So, pretty significant, but various depending on what marker you look at.
Okay.
Right? But in vitro, that just means in a dish, in a experiment, or in vivo, in mice, right? So we were able to systemically downregulate it, right? Yeah. So discovering this, I was thinking to myself, and in philosophical discussions with the researchers at the NIA, I was thinking to myself, like, well, is there any way we can figure out if we can use the same material, not only to downregulate inflammation and maybe take care of some diseases that the FDA or EMA designates, but as a preventative measure, getting back to what you were talking about before. So this is kind of like my moonshot, right? If I can prove that using the secretome or the proteins from these super early cells, which is sending out very potent regenerative messages, into your body, can we slow down, stop, or reverse biological aging? Right. And so that's my hunt right now, is to find the right gauge to say, yes, we're moving the needle on biological age. And if we can do that, a 35-year-old Joe in San Diego can then, as a preventive measure, be able to inject these secretome from the human trophoblast stem cells at the right dose and the right frequency, and hopefully be able to keep his internal organs at that 35-year-old age. So when he's 100, he still will have internal organs of a 35-year-old. Wouldn't that be interesting? That's how you stave off a lot of disease, right? Because your immune system is extremely robust at the time, and you still can fix a lot of things. So my goal is maybe in the next 10, 15 years, create a product for prevention so that everybody can access it. And because of the scale and the immune privilege of our human trophoblast stem cells, I want to mass manufacture this for everybody to use and have it be cheap enough that anybody can use this.
How cheap are we talking?
Very, very cheap.
Yeah. And that's because of the nature of the human trophoblast, as you said before.
Mm-hmm.
It's something that mesenchymal or other stem cells are not going to be able to work. It's going to reject.
That's right.
Stuff. Okay.
Yeah. So there are two main types of stem cells. Ones that are immortal. That means like human embryonic stem cells, or even these induced pluripotent stem cells, or iPSCs. They're immortal. That means they will continue to grow. They don't stop. Unfortunately, cancers also do that, right? Then there are naturally senescing cells. So every cell in your body, except for those, embryonic stem cells, will senesce over time. They get old and they will die off, right? And MSCs, they have a population doubling about 25. So they can double about 25 times and they'll stop and they'll apoptose, right? But with ours, we can go 85. So we can go pretty far. And with that kind of scale, we believe we can get the pricing down to, my hope is to get it down to maybe the cost of buying a bottle of aspirin or something. Yeah. Right.
What about like telomere shortening? Does it affect that?
Yeah. So telomeres shorten when your cells divide. So I like to describe it as like, imagine you have an Oyster card, right? And it has certain amounts of tickets inside. Every time you use it, it decreases a little bit. When for cells, you use it when you divide. So when one cell becomes 2, you take a little bit off the telomere. Does it again, take a little bit off the telomere. And when the telomere runs out, it apoptoses. The cell signals itself to like, all right, time to die. We're done, right? And so that's also one of the strategies that scientists are trying to use to say, hey, what if we can extend the telomeres? What if we can make them not shorten or get cut off so fast, right? So these were strategies for longevity that other people are working on. Very exciting stuff.
Yeah. I'm thinking when you said these cells are immortal, right? The embryonic cells, or the human trophoblast cells.
Yes. Human trophoblast stem cells are not immortal. So they are naturally senescing cells, but we're able to push them out pretty far. Gotcha. It's the human embryonic stem cells, the original cells that became us, and then the iPSC. So these are the cells that the Japanese or Shinya Yamanaka used to push all the way back to the original stem cell state. They're immortal. Immortal cells are a little problematic to use for cell therapy sometimes because how do you know that every cell has been differentiated? When you're differentiated, they become naturally senescing cells. But when they're undifferentiated, they're still immortal. But cancer cells are also immortal, right? So that's pretty scary. So this is a problem with using a lot of these immortal cell lines in your body, is that it may create a secondary tumor.
What keeps you up at night? Like, what are the key challenges that you face currently in this space?
It's a really great question. Time. Time. That's it. The FDA and the EMA, they're built on sick care. Okay. And for us to get through the whole system, it takes years, sometimes decades. And, for us to want to get this therapy to everybody fast, we have to get through the system because the FDA and the EMA still has a monopoly over patient access, right? So I'm a very big proponent to hopefully suggest to the FDA or the EMA that they need to create a different section, a different pathway for prevention care, because that's really the one path that will significantly affect how our health spans. Brian Kennedy likes to say, when you have a homeostatic system, like our bodies are healthy, right? Once it starts breaking down, it's really hard to bring it back. So you're better off just keeping the whole system healthy the whole time, right? And I love that. So, and I think that that's the key. If we're young and healthy, let's keep it that way. Yeah. Right. And so we're able to use these early potent signals from these human trophoblast stem cells as a prevention therapy in, whether it's IV or other forms of administration. We're able to keep our body in this healthy state and keep it from getting sick in the first place. And that would ultimately be so much cheaper, for society and for individuals.
It sounds great.
Yeah.
Why am I not being IV'd with it right now?
Because we have to get it through the system. We have to get it through the FDA, and we have to pick an indication or a disease or a sickness that the FDA deems to be a proper indication, a disease or a sickness. And so we're looking into chronic fatigue syndrome. We're looking into many other things like sepsis, et cetera. But they're very, very hard problems to solve. And so we need a lot of scientists with the domain knowledge to help us carry that all the way through. So we're working on it.
Okay,
Can I ask you a question?
Go for it. Yeah. Go for it. Go for it. Yeah.
Right. Julian, if you had access to a therapy like human trophoblast stem cells, would you do it? And what would make you want to use it as prevention?
Yeah. So I remember back in the day as a 21-year-old,
yeah,
I remember being at college and you'd just go out, lights out, and you just wake up the next day with a bit of a hangover and then just carry on your day and go to lectures and all that. You'd just feel a bit invincible. That's and then you would just be able to do that 20 days in a row, whatever. Like it didn't have to be drinking, but you were just constantly on the go doing things.
Right.
I miss having that crazy abundance of energy.
Right.
And I'm very energized now, don't get me wrong, but I've optimized my life in a way to allow for that rather than back then where I was eating shit and all that. So I think the main reason for me would be just to be just energized and in myself and be as present as possible and to be able to, just to do the things that I want to do with that high level of energy. I think the thing for myself is whilst I sit in this longevity space, I would say I've got a pretty low risk appetite. And so for example, I haven't taken peptides. I haven't done anything that's, let's say, level 3 or 4. I've been focusing a lot on level 1 or 2.
Right.
Probably because I'm 33 and I don't feel this strong need to, and I'm energized enough.
Right.
I don't feel this strong need to put myself into a compromising situation.
I got you.
So I don't want to be a first or second mover. I want to be a third mover.
Gotcha.
And make sure that, it's been proven out and all that. So I think that would be my biggest pushback to going deep on stem cells now.
Yeah.
But I'm so excited for more of the literature and tests to come out and to prove things as well. So I think from what you say, it makes a lot of sense. I'm interested to, because I had Matthias Bernau from Cellular Labs recently on the podcast, and he was speaking quite a bit about some people that have, including Brian Johnson, who's already taken his MSCs, and it all sounds very promising. And I think with the scalability of the human trophoblast stem cells, that sounds really exciting as well.
It is. I only work in one aspect of it, right? So I'm always curious, and if you don't mind, I'm going to ask you another question.
Go for it.
So you talk to a lot of people in longevity and in different areas of science, right? So do you have a sense of where the solutions for longevity will come from? Do you have an idea? Do you have a gut feeling?
I think the biggest issue right now is that there are so many bets being placed on what might work.
Right.
And so, like, right now, we don't know.
Right.
What will be interesting is if we do have something or a combination of a few things. It's going to be a combination. You speak to people like Matt Kaberlein and Peter Diamandis with the X Prize, and a lot of people believe that to get to that 20 plus years of healthy life extension, it's going to be a combination of a few things. And so I don't think it will be one thing that will get us to longevity, escape velocity, or that biological immortality, but a few things. And I definitely see things like stem cells being one of those things.
Absolutely.
What would be interesting to see is like how personalized it has to be, that protocol. It'd be great if we just have this amazing protocol, and you've got the accelerated bio thing and this and that, and that every person in the world can then get to that escape velocity. But
absolutely. I'm actually one to believe that everybody should in their own way try to approach longevity and try to create solutions for it, because a lot of these solutions are not mutually exclusive, right? I think as human beings we tend to be very linear thinking, and everybody's like looking for the silver bullet. Oh, it's got to be that way, or it's got to be this way or that way, and they're arguing against each other on which way is the best way. I think everybody should just go at it, open up the whole field. Everybody just, go with the strategy that they believe will work for them. And if we succeed, if any one of us succeeds, then everybody will benefit. And that's the best part about it, right? So, I think definitely more collaboration and less arguing. Fighting over the little things, they just don't seem to make sense for longevity, because we're all aimed towards the same direction, right? So I really do think that especially with in your platform, get everybody to open up their minds and be flexible and hear each other out and support each other. I think that's great.
I get a lot of pushback sometimes from comments saying like, this is the devil's work, and this is just for the billionaires. That's the most common pushback.
Right.
Like, all this stuff that you're talking about is just for the billionaires.
Right.
What would you say to them?
In the beginning, it's always very expensive. Just like in gene therapy, the most expensive gene therapy is 4.2 million. It's insane, right? No one can afford that. But it's actually to save a baby. So what do you do, right? But it's a one-shot deal. Your problem is solved. You literally go in and edit that one gene that mutated, and your problem is solved, and forever you can live happily and healthily, right? Yeah. Now, in the beginning, any technology is super, super expensive, right? But then it goes through that process where the economies of scale will come in. Yeah. And so that's what I'm trying to push, right? Is that, okay, cell therapies, gene therapies, they're very expensive right now, hundreds of thousands of dollars. Only the very, very rich can afford it. But with the scale of our platform, I want to make it available for everybody.
What's the timeline on that?
15 years, maybe.
Okay,
10,
so it's
years.
like okay.
It's as close to the longevity escape velocity goal that everybody seems to have.
Yeah. So the cell and gene therapy space back in the early 2000s went through a few blows, right?
That's right.
There are a few deaths that happened, and it really pushed the space back quite a bit.
That's right. That was gene therapy. Yeah.
Gene therapy. Yeah. Okay.
That was really, really early days, and I think the scientists have learned a lot since. The scientists and the doctors have learned a lot since. Yeah. And so we know how to better control these products, or control the engineering of the products, and also the manufacturing environment, et cetera. So it's been 20 plus years. So lots of improvements. So
Yeah.
I don't think that's much of an issue now. It still can happen, and it still does, but I think people understand it to be just part of the process.
The reason why I bring it up is not to put the space down at all. It's just to say like how one grows.
Yeah.
It's so you want to evolve the space. You want to bring these therapeutics to market, but I'm sure there's a tight balancing act.
That's right.
Moving fast enough.
That's right.
But also with intent and with that in mind.
Absolutely. Yeah. Moving fast is definitely very, very key, especially for longevity, right? But the unfortunate thing is that we don't know everything about biology yet, and that it's so complex that it's very difficult to figure out. Even long-standing chemical drug processes, people still have toxicities in their liver, neurotoxicities, et cetera. So, and people still die from that in clinical trials. So it does still happen. But I think, with the advent of AI coming in, with the advent of automation, we can really make very big strides to understand biology so much faster. I mean, it's going to accelerate extremely, extremely quickly. And hopefully we'll be able to find some of these solutions, in the next 5-10 years. I'm very excited about that, by the way. I think because human beings, we're very linear, like I said before. AI will be able to give us that breadth of vision to see how everything's interconnected with each other. And that's going to help a lot for biology.
You say 5 to 10 years. I would love to go into your crystal ball of what the world, especially related to stem cells, will look like by 2030, 2035.
Wow, that's a really great question. I think by 2030, 2035, 10 years from now, we're going to have more and more gene therapies. So to treat at least monogenic diseases. This just means you have one genetic mutation that's affecting your life, right? It could be death, it could be, lifestyle, etc. A lot of them are going to come through the system, and I believe that a lot of people are going to benefit from that. Cell therapies, definitely, and the prices are going to come down. I'm hoping that we will cure cancer by then, and especially with all the immuno-oncology, coming online. Immuno-oncology just means using your own immune system to go after cancers, right? And I believe that by 2035, we're going to see a lot more cures, which is going to be pretty amazing, like actual cures.
Yeah.
So
you're a Buddhist.
I am.
And I love the fact that you're working on this you're working in this incredible space, but you're a very spiritual man as well.
Thank you.
How do you look at the ethics of all of this?
The ethics. Well, I don't, because of the source of our cells, we don't have to address that at all, right? Relative to, the ethics of using other cell types, I'm actually quite agnostic to it. I think that saving lives is more important. And so I think I will, as a Buddhist, I actually live it more like a philosophy than an actual religion. Yeah. So for me, it's very, very different, and it's very personal. So I don't literally adhere to a very general religious kind of sentiment. So to me, it's very personal. So the ethics part, as long as we are not hurting anybody, it's good for me.
Okay.
Yeah.
Yeah. I think eventually we'll get into the conversation of this space and scientists trying to play God.
Right.
I think that ethical question will probably happen or come sooner.
Sure.
Rather than later.
Sure.
What happens then? Because I feel like we'll probably get to the point where these therapeutics come to market.
Yeah.
But it's actually going to be human intervention.
Sure.
That'll be probably the greatest barrier, I would say, to getting it into market, right?
Right. Yeah, absolutely. It's all human. The whole system's built by humans, and therefore, we control it all. I actually think that I'm pretty extreme in this matter. I think that death is bad in general, so let's just avoid it, right? And a lot of the sicknesses that we have from getting old, we can try to prevent. And if we can prevent it, or if we can cure it, let's go do that, right? And, I have these philosophical conversations with people all the time. So, I ask people, well, do you want to live forever, right? And my answer is always yes, absolutely. And it's quite simple because I don't want to go through the process of being sick, and I don't want to die from it, right? So it's very personal to me because both my father and mother have gone through cancer twice each. Once in their 60s, once in their 70s, and so I can see the predisposition of cancer in my family, and that scares the hell out of me. And being chronologically 53 this year, I know that's going to happen to me in the next 10, 15 years. So this is why I have such an urgency to do what I can to solve a lot of these problems, and the only way to do that is to have multiple shots on goal. So I want all of the top scientists with the domain knowledge to take my platform, literally just take it, use it, try and solve some problems, cure cancer, cure diabetes, go cure Parkinson's, many things to do, right? So I have the right stem cell source, but I don't have the domain knowledge nor the patient access to do that. And so I want to make this available for everybody so that in 10, 15 years time, we can see multiple therapies on the market that will hopefully help us one day.
Are your parents still alive?
They're both alive, luckily. But I've seen them go through the resection and the chemotherapy, and it is not a pretty sight. And so they're definitely trying to make sure that doesn't happen to me, right? Yeah. And I really do believe that everybody should adhere to that rule, meaning if anybody asks you, do you want to live forever? The answer is always yes. And because the people that say no, they're saying it out of luxury of being healthy at that moment. So imagine, Julian, if your doctor came to you and said, Julian, you only have 3 weeks to live. How would you react then? Yeah. Right. I think all of your survival instincts would kick up, and the only thing you want to do is survive. Right. So given that endpoint, that the answer should always be, yes, I want to live forever. So that's what we should all try to achieve. Make it an option. Make death an option.
As our friend Jose Cordero will say.
That's right. Immortality.
Yeah. I think right now the biggest pushback to this space is that we have a very niche group of people that are saying something.
Right.
And I know those people, they really want everyone to be healthier, happier, live longer, potentially live forever, or have choice.
That's right.
Over how they die rather than suffering with that. What do you think is going to be the key thing for us moving the needle forward when it comes to, I'm not going to say the mainstream, but to get more people involved and on this journey?
Right. I think it's already happening, and it's happening through platforms like yours, getting this message out to everybody, right? And platforms like Brian Johnson, or even some of the scientists that are constantly on YouTube and on different platforms talking about longevity. I think it just takes that, and I think the movement's already catching, the momentum, and it's accelerating, which is very exciting because, it's quite practical, but any of these therapies really require investment. It's not going to happen by itself, right? Yeah. And so my big ask to everybody is find a way to invest in longevity, especially if you're a billionaire. I mean, what is beating the S&P 500 for the next 15 years going to help? Nothing. You can't take it with you, right? So, if you are a high net worth individual, put a very big chunk of it in longevity. And now you can bet on any strategy you like, so it's strategy agnostic, right? But there are a lot of different companies doing a lot of very exciting things, and they will need funding to get it through the system. And so everybody, especially if you're over 50 like me, focus on longevity, put your money to it. Now, pick your strategy that you love, go with it, but do something. Don't sit around and just make more money. That makes zero sense.
Yeah.
Right?
God, you got me thinking there. That's like such an important way. And how do we communicate? So, for example, how often do you get pushback from your Joe in San Diego or Emily in San Francisco, my usual archetypes, about like stem cells? You must get it so often that people are like, because stem cells is such a triggering word.
It is, but I think it's just a lack of understanding of what it is, and so conversations like this really help, where we're able to just tell everybody out there, hey, this is actually okay, it's safe. If done right, it's safe, right? And it's available. So we just need to process it and get it through the system. And so, the more of these conversations that you have with people and that I have with people, the more understanding that the general public will have with stem cells. And that will drive the cell and gene therapy movement to create more cures for the human race. And I think that's all very, very positive. Unfortunately, it does take some time and investment, like I said before, but we're moving in the right direction, which is very exciting to me.
So just to round off, if someone wanted to get injected with human trophoblast stem cells at whatever cost, when will the first person be injected?
We're hoping to get to clinical trials probably within the next 2 years.
Okay.
Right, in the US. For something related to inflammatory disease. So, but that's to be announced.
Okay.
At a future date. But we're going as fast as we can.
Yeah.
So.
And what advice would you give to someone looking to get into the space, or anyone who's looking to venture into longevity?
That's a great question. If you're a scientist, come out and start a company. If you're a business person, find one of these scientists and start a company. Raise some money and chase after a strategy that has to do with longevity. That can be anything. And if you want a platform to use, come talk to me.
Yeah. Brilliant. Yuta, thank you so much, as always.
Thank you so much, Julian. Fantastic talk.
Hey, thanks so much. If you want to know what tomorrow has in store like I do, you definitely want to listen to our recent episode where I talked to Peter Diamandis about a future where we could live forever. Thank you so much.